Okay, everybody hear me? So I'm Peter Milne. I'm a technology architect at Adform, and I'm going to tell you how Adform does some of its work in .NET to achieve high load. But before I start, I want you to raise your hand if you are older than 40 years. Okay, so I've got about 20 years on at least all of you. So, my background is that I started in the IT game. Hang on a minute, my audio's weird. I started in the IT game in the 1980s. I was a junior programmer on the first commercial email systems, so email is partly my fault. What I want to do today is talk about some computing history from my perspective. Then we're going to talk about some high-load definitions, a bit of computer science. We'll do some discussions about Adform, how we deploy things, how we use a private cloud, what AdTech actually is, so two elements of that. I'll talk about .NET Core, some big data storage that we use, and I'll give you some Uncle Pete's advice. So, computing history. When I started in Windows, it was 2.1. It was a 16-bit cooperative multiprocessing environment that ran on a PC. I read this book by Charles Petzold, Programming Windows, on the train as I was going to work. And then when Windows 3.0 came out, I reread the book. We used to code in C, and we had a massive event loop, which you'll see just here. And we used a tool called QuickC. And yes, these are floppy disks. You would get a distribution, it would come to you, and it would be a number of floppy disks. And it could be 2, it could be 5, it could be 30, and you would insert them one at a time to load your software. It was painful, but it was exciting too. So does anybody know why Windows took off? Why it was so wonderful? Okay, no. Let me tell you what it was. Windows 2.1 cost $500 per seat in the 1980s. To give you an idea, my house mortgage was about $300 a month. When Windows 3.0 came out, they changed the license price from $500 to $50, and everybody bought it. And that's why it rocketed ahead. So let's look at some history according to me. In 1980, when I first started to code, I punched cards to put my source code and my data in, and I ran it through a card reader in DEC 10, and it was batch. So we had batch, and in the 70s, we got interactive programming where you could sit at a terminal and do something. So in the 80s, we got SQL and graphic user interfaces. Towards the end of the 80s and into the 90s, we got client server, so distributed computing. I did my first RPC call in 1990, and I thought it was absolutely magic. I thought it was the most magical thing that I could ever see in my entire life. Then in the early 90s, we got object orientation, which could have been a wonderful thing, or it could be a terrible thing, depending upon your perspective. You know, a fool with a tool is still a fool. So when objects came along, everybody thought that they could program really well. Anybody know how big the Windows Notepad code was in Windows 3.0? It was 32K in size. If you took that Notepad code and recompiled it with the Microsoft Foundation class that arrived in the early 90s, it became 360K in size, 10 times bigger. So we could talk for a long time about the way you do OO, and that was probably the wrong way. We also got the web in the 90s. So when I researched my master's degree, I used to sit down at a Netscape navigator and I would search what was available on the web, which was 3/5 of nothing. We also ended up towards, in the early 2000s, we ended up with things like this, mobile devices, which is a new kind of dialogue that the user has with the system. The portal to the system is this little screen. The dialogue is a set of gestures and conversations, and that portal communicates to a set of services that sit somewhere out in the world. Okay, in the 2010s, we ended up with big data and the old notion of machine learning. So machine learning's not new. In the early 90s, when I was doing my master's degree, we did neural networks. They were really tiny. They ran on my 486 computer. It took 2 weeks to train a data set. My kids would look at me and say, "Dad, can I use the computer?" And I'd go, "No, it's busy." And that's what we did. In those days, you couldn't build a computer big enough or a neural network big enough to do anything useful. It was all theory. Let me talk about ancient projects. In the past, the problems we were trying to solve were small. They were simple. A few people worked on them. They ran on one big machine that had one core. There was one programming language. There was one business analyst who would tell you what you needed. And yes, this is COBOL, divided into its procedure division where the code ran, and the data division where the data was stored. So we're talking about read-only areas, segments of memory, and modifiable data areas. The problems were easy. They were mostly accounting things. They were simple to do. So you see my Towers of Hanoi animation going over there. That's the sort of thing that you program for. That was the most exciting thing because you used recursion. But today, the problems we solve are much more complex. There's literally thousands of developers working on the problem. There are thousands of use cases, stories, if you like. There are many business analysts working on it. We have lots and lots of features, lots and lots of languages. I know you're all .NET people, but you probably code in more than one language. Oh, by the way, Microsoft didn't invent a common language environment. It had been done much earlier than that, but it was reinvented when Windows NT came out. Okay, what else do we have? We have lots and lots of data. Data gets stored in different places, and we have literally thousands of machines at our disposal. For almost no money, we can build an application that can run on literally thousands of core. We can use Azure, or we could use AWS or DigitalOcean, and have these machines available to us for almost no money. So the problems we solve today are much more complex and much harder to do than they were 30 years ago. So what else has changed? Well, the number of transistors that you have inside a CPU. Everybody's familiar with Moore's law, that the number of transistors in a large-scale integrated circuit doubles every 2 years. When I started, I used an Intel 8085A. It had 6,500 transistors in it. It was an 8-bit microprocessor before Intel was famous. It was really cool. You had an accumulator and you had a few other registers and you did all the stuff yourself. You programmed in machine code. I still have the book and the assembly card for it. Today, you can buy an Arduino Uno that has, 8 times the number of transistors in it. But in a modern machine, if you look at the Intel Broadwell chipset, it's got 7 billion transistors in it. And the Apple A10 has 3 billion. So our capabilities are more vast. Sometimes that makes us lazy because the CPU runs fast. But This is what the modern world is like. The other thing we have to face is distributed computing. Everybody familiar with the CAP theorem? Yep. If you're not, I'll give you a quick lesson. Consistency, availability, and partitioning. You can only have two of those things in a distributed system, and you have to sacrifice one. So when your problem gets bigger than one machine, the CAP theorem becomes involved. Regardless of what types of transactions I'm talking about there, whether it be a database transaction, whether it be a clustered database transaction, whether it be a whole bunch of machines working in concert with each other. We also have high complexity. So what's high complexity? Okay, usually we're trying to discover signal inside of noise. If we all talk in this room together, it sounds like noise, but it's actually signal between each of us. So some of our problems is we're trying to discover signal in noise. So how do you know when something's highly complex? Try explaining it to your mother. And then you'll know you've got a complex problem. And the other line to it is that if it was easy, anybody could do it. So, let me show you what high load is. Watch this video. It's about 10 seconds long. How many people did you see? I think 250 is what I guess at. So I took that video while waiting for a colleague at Shinagawa railway station in Tokyo. And just like everywhere else in the world, they use a transport card. And you have to touch the gate to enter a certain section and touch it to leave a certain section, and you get billed a certain amount of money. So there are 12 gates in Shinagawa, and that was 10 seconds worth. So you can see this is high load. A lot of events are occurring when you touch those transport cards on the sensor. So if you're going to have high load and you want velocity, velocity is all proportional to latency. So latency is how long something takes to get done. We can talk about network latency, how long it takes for a packet to get from one place to another. We can talk about round-trip latency on a web request and a response. That's a big latency. We can talk about latency to the storage layer, through a database, down to the disk or to the SSDs. Add all those latencies up, and that becomes your velocity. Then if we want to think about throughput, scale is throughput. So it's like power. It's work done over the time taken. So the throughput of your system is a measurement of its power. And then we want to have availability, always on. So think about it. Telecommunications, electrical supply, water supply, sewage supply. Interesting thing about sewage supply, when we think in an emergency situation, we go, yes, we need water and we need flashlights. But let me ask you a simple question. Would you prefer to die because you couldn't drink or because you couldn't poop? Okay. For the young ones, of course, always honest things like Twitter or Snapchat or Facebook or Netflix, or the stuff you expect when you pick up your phone and you expect to have an automatic online translation and your location on a map that tells you where you want to go. We now expect these things. That's high availability. All right, so I've given you some definitions. I've been very, very quick. I'd like to have long conversations with you afterwards, but I've got a limited amount of time. So I'm going to talk about Adform now, what Adform does and how we do it. First up, I'll talk about our private cloud. We don't except in South America, we don't use a public cloud. There's a bunch of reasons for this. The reasons mostly have to do with legal reasons and an economy of scale. At a certain point, when you scale up to a certain level, it is less expensive for you to buy the hardware and build your own data center than to use a public cloud. But it has to be really, really, really big. So we've got 1,600 bare metal machine in 7 data centers across the world. We build our own private cloud with OpenStack. We have a whole bunch of VMs that run, we have hypervisors that run, and we have a team of talented people who know how to get that stuff done. You don't have to worry about it as a developer. It's almost, I was going to say it's almost like using AWS, but I tell a lie. I'd like it to be as easy as using AWS, but not quite yet. So this is where they are. We have 1 in Vilnius, 3 in Copenhagen, 1 in New York City, 1 in Hong Kong. Where else have we got? 1 in Singapore, and we have a cloud provider in Sao Paulo. The reason we use a cloud provider in Sao Paulo is because we don't have the scale there yet to justify it. This stuff's connected together with dark fiber, which gives you incredibly low latencies to the point that if you have a clustered database, for instance, that has failover between the clusters, you can put half your nodes in one data center and half your nodes in the other, and they think they're all on a local network segment. Quite nice. So that's our hardware. Let me talk about real-time bidding. So you're familiar with the idea of going to a website and seeing an advertisement on the website. In that red box over here, I'm standing in the way, in the red box is an ad that's being presented to you. That space is sold by the publisher of the website. That's why all the stuff on the internet is free, is because advertising pays for it. The space is called an impression. And what happens is when you're about to display the website, what's the best way to describe it? An auction occurs where the impression is auctioned out to the highest bidders to see who wants to present the ad. This is the way it works. So you have a publisher on this side and goes through this magic over here through an exchange, and a demand-side platform, or a DSP, receives a bid request. In that bid request is some information about you. Maybe the device ID of your device, or a cookie, your geolocation, your browser type, the size of the screen on your browser, your IP address, a whole bunch of stuff that identifies the user of that particular website anonymously. So we're not Google. Google knows everything about you, okay? Google knows what you look at in the privacy of your own home at night. Google knows everything. We don't. We just know this anonymous information. So that's sent through to a bidder service, and a whole bunch of people all over the world bid to place that ad. So we get 1.2 million bid requests per second. We respond in about 50 to 70 milliseconds. The value of the auction at any 1 second in time is about €1 million. That means for sale, there is €1 million worth of advertising to be bought by an advertiser. Of course, we only bid on about 30% of those, and we win only about less than 1% of them. So how do we do this? Well, we have an Nginx load balancer that takes the bid requests. We have 12 of them. But we have some bidder servers written in .NET. We have 102 of them sitting in various locations around the world, replicated many times. These take the bid request. They choose whether we're going to bid and what we're going to bid with, the price and the actual creative we want to display. How do we do this? Well, we have a big cookie store. We store billions of cookies with device IDs that identify you anonymously. And we profile them into audiences. In order for us to obtain a cookie about you, we need to do it very quickly. So we use Aerospike. It's a highly scalable, low latency key value store, and we can get a read or a write out of Aerospike in just under a millisecond. So it's not quite RAM speeds, but it's pretty good. About November last year, probably a year ago last year, the CEO of the company and the CIO of the company walked into my office with long faces, and they said, "We're having trouble bidding. Can you fix it?" And I went, "I fucking don't know how to fix it." But I called a few people, and the problem was that we had a high latency. Not in discovering who you were, but in the time it took us to decide what to bid. Essentially, the bidder has a set of filters, and it goes through, is it male or female? Are they over 50 or under 50? Do they speak English or do they speak Russian? You know, those kind of filters, down to, are they interested in cats or are they interested in trips to Frankfurt? The cause was these filters were actually implemented in the .NET dictionary, a great, wonderful hash table implementation. So I'm not saying it's bad at all. The point being was we had pushed it beyond its design. No matter what we did to tune it, we couldn't make it any faster. So we went back to first principles in computing, and the guys built a fixed byte array and did binary searches to do the same equivalent thing. So we used a little more memory and a little more tricky code, and we reduced our latency by 67%. So even if you've got a really good tool and you need performance, you might have to look at exactly how the tool works. Okay, on the other side of things is our data management platform. And there are people in the audience who can tell you exactly how it works, so I'm going to go over it quite briefly. Essentially, we find something to track you with. So if you have a look in the developer tools in your Chrome, you'll find that you might see a cookie from Adform, and maybe one from, say, Google, and here's a couple from DoubleClick. They're all tracking what you're doing. You've given permission for these things to happen. So what we do is we gather all of that information and we divide or we categorize the cookies that we have into segments. We gather all of this information, we process it, and say that Peter is interested in helicopters and Arduino programming and Pornhub. Not really. I'm not interested in Pornhub. Nobody is really. So we have a whole ton of these things. We have 5 billion of these cookies, and we have 250 billion cookie segment pairs, so the matching between things. We use this data in our bidding process. So we get all this data, we buy it from some people give it to us for free, and we analyze it with MapReduce style techniques to allocate a segment that you're in. So this is a monstrous architecture on the left-hand side. Actually, Roman designed this architecture, so I blame him. But to make it work, we use an API approach. Once again, most of it's written in .NET, except for the Spark parts of it. Most of it's written in .NET. We use a a Lambda architecture for the data flow itself, but we use a Kappa architecture for the real time. And if you're not sure what Kappa is, it's a log structured write. So it's always an append, immutable append. We got tons of technology in our DMP, too much. It all works, it all makes money, but it's hard to maintain. So we have to minimize it. So over the next, I guess, year and a half, we'll be building version 2, and we will reduce the number of technologies, probably get rid of the grey ones. And I say probably because tomorrow we might change our minds and keep the grey ones and throw the white ones away. The biggest problem is being able to ingest and process large amounts of data at once and to debug it. There's lots and lots of moving parts here. And so we analyze through patterns of data flowing through our systems, and Grafana tends to be our good friend. Okay, so I've given you an idea of how big Adform is, what sort of stuff, how many things we do a second, how much data we ingest and process. It's big. Really, 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 really big. Bigger than you could ever imagine. Let me talk about .NET Core. Inside of Adform, we have just dipped our toes in the shallow end of the .NET Core swimming pool. Our API gateway that our customers use is written in .NET Core. And our audit log, the thing which allows us our audit log service where somebody makes a change to a business object, we want to make an audit on that, that's also written in .NET Core. So why do we bother? Why would we bother going to .NET Core instead of just .NET? Well, first of all, it is really, really, really uncomfortable to run a Windows VM on top of Linux. It's just makes you feel stupid, and that's wrong, you know? You do it, and it works great, but you just, ugh. The second thing is we want to preserve our investment in our .NET skills. So there are some things to consider with .NET Core. .NET Core does not equal .NET. So if you do a system call in your application, or something that does a system call that is part of Windows, then it's not going to work in .NET Core. Okay? So only you know the details of that. So what did we have when we first tried to use .NET Core? What were the annoying things? What was the terrible thing? Well, not much, actually. I've got a list of them on the screen, and they're little nitpicky, trivial annoyances. So this is in a project of 350 man days, and we wasted what? 4 days at the most, 3 days at the most on the nits of .NET Core. So what I want to illustrate there is that moving to it for .NET people was reasonably painless. It didn't slow us down at all. In fact, in this project I said, okay, we've got a cutoff point. When you get sick of it, we'll just switch back to .NET. And they didn't get sick of it. So what do we get from .NET Core? Platform independence. We got these things. We might want to run on that, and I don't know. You know, .NET Core runs on a Raspberry Pi. I'm not sure Adform is going to deploy a lot of Raspberry Pis, but it gives us flexibility for processes and systems that run in the future. This is the most important thing to us, is retaining the investment we've made in our software engineers. Talented, strong .NET people that we want to retain and give life to. One day in the future, I hope that we can move to containers and replace VMs. We don't have a plan for it, so those of you who work for Adform, don't go back and say, Peter said we're moving to containers. I would love us to, because you can use the machine resources a whole lot better, but that's the way to get there. It gives us a bit more performance and scalability too. That's what we get. Okay, I'm going to skip through the big data storage really quickly because I want to get into Uncle Pete's advice. So we have HDFS clusters. Everybody calls them Hadoop, but it is just storing things in HDFS. We have a bunch of things that we process to map-reduce data in those. This is what we found comparing Hive to Spark. We found Spark is faster, uses less machines, and uses less space. We have a column store called Vertica, which is a scalable column store, allows us to do multi-filter queries and scale them. And we have a row store called Aerospike, which is just a big hash table. It's like a big dictionary. You give it a key and it gives you a value. Or you do a put to it and it puts the value. But it's massively scalable, gives us a millisecond latency. We use Kafka. We use Kafka as our circulatory system. So we process about 1 million messages per second in our Kafka clusters. This is data flowing around parts of the organization. So I've given you an overview, and now I want to take just about 5 minutes and give you Uncle Pete's advice. Okay? I'm old. I've made all of the mistakes. Some of them were really big. Some of them were absolutely terribly embarrassing. You will make 1 or 2 of those in your career. So the first advice I'd like to give you is that use Kafka. If you're going to flow data around, use Kafka. Data is like the blood in your organization, in your system. Kafka is the circulatory system. And Confluent, which is something that sits on top of Kafka, is a healthy lifestyle. So why do we go to Kafka? The bottom line is this. Before, when we had to do some data integration, a single integration used to take about 3 months. Today, you can just tap into the flow and use that data anytime you like. So if you're going to look at data storage, if you have a row problem, a massive row problem, row-oriented data storage, use Aerospike. Don't bother with Cassandra. Don't bother with scaling up Redis. It's too hard. Just get Aerospike. If you've got a big column store problem, and I mean a big one, Vertica is incredibly expensive, but super valuable. It solves the problem. If you deal with raw data, big data, store your files in Parquet instead of comma-separated values. You'll save about 30% of your disk space. And I've shown you that Spark runs about 20 times faster than Hive on the same hardware, on the same data. Some things to watch coming up in the future. GPUs, graphics processing units. They're really cool to play games on, okay? But I didn't tell you that. What is interesting is that we have some columnar databases coming along now that use GPUs to do the queries. For instance, ScreamDB, you can put terabytes of data, about 50 to 100 terabytes of data, and do a query on it, no indexes, and it'll be done in under a second, depending upon the query. Multi-predicate, multiple filters, the worst SQL you could probably imagine. Same with MapD. They tend to do it a bit differently. They're all in memory, and so you need a bit more memory than Scream does. Deep learning. Who knows what deep learning is? Neural networks essentially is what deep learning is. So you've got this wonderful TensorFlow technology made available to us by Google. And Theano is another one. They both take advantage of GPUs. Other thing to watch is persistent RAM, Intel Optane. Up until now, all of our software runs on RAM or dynamic RAM that disappears when you power it off. This will revolutionize the future. Check it out. Okay, I want to talk about enterprise and open source. Open source does not equal free, but it's cheap. Okay, it does have a cost. It's the modern version of escrow. I recommend that you fork the repository of your open source and learn how to build it. Because what happens if the people who are backing it don't in the future? You want to be able to survive on your own. Enterprise is value for money. It gives you a neck to choke. When Oracle bought Sun Microsystems, there was a neck to choke. We could go to Oracle with our problems instead of going to Sun. Okay, your development process. Implement continuous integration and delivery. Build yourself blue-green feature toggling in production so that if you introduce a new feature and you've absolutely, totally screwed up, you can switch it back. Have a DevOps culture. Think about how this is going to run in production. Rather than the code looking brilliant, how's it going to run? Hire good people, not entitled princesses. Good people will make you more money than some Silicon Valley princess. Let me talk about Agile for a moment. Agile is a frame of mind and a technique for you to build software. Agile is not an excuse for losing track of things, being disorganized, having a short attention span, and it's not a club, a social group, or a cult. So there's no religion associated with it. So, anything you haven't tested recently will break. If you don't have good test coverage and you wrote some code 3 years ago and you haven't tested it, it's probably broken all by itself. That's entropy. Retrospectives. Work out what went wrong, work out how to do it better, and refactor it. Always fail early, fail fast. Watch out for the superhero. Everybody likes to be the superhero and put the underwear on the outside and the towel behind you. But your superhero, if you depend on them, will go on vacation, have a baby, get hit by a bus, leave the company. So don't have a dependency on a superhero that does everything. Okay, stupidity. We're all a little stupid, but it's not a competition, okay? When you got this really great idea, check with a colleague to see if it works. And then just, whatever you do, don't just code it and put it into production. Okay, take a look at this bike lock just here. The solution should be as simple as possible, but no simpler. The bike lock works perfectly, except for the corner case that nobody thought about. And a hypothesis. If you have a great idea, you must be able to explain your idea exactly to your peers and have them help you prove it or disprove it. To get scale, to get high load, you need to use parallelism. Parallelism opposed to concurrency. If you're not sure what the difference is, I'll tell you now, use the least amount of concurrency and the most amount of parallelism to get scale. And finally, nothing beats running code. Doesn't matter about your team spirit or the design methodology or the agile methodology that you're using. Nothing is more important than running code. Someone is paying you to deliver some value, either a commercial value where people make money, or if you're in the government sector, it's a social value where the race is improved, but somebody's paying you to do that. So I've run through that very quickly. Does anybody have any questions? Green shirt here. He wants another prize.
Thank you for a great talk. About Vertica, there is a Russian alternative, ClickHouse. It's capable of handling petabytes of data. Unfortunately, I don't know about their plans on GPU. Sorry. That's all.
That's interesting. That's interesting. New column stores are particularly interesting.
ClickHouse.yandex, it's free and open source, so you can try it.
We will. One of the other things you have with any level of legacy is that you have to go from the old to the new, and somebody has to fund your movement. So yes, I'm looking at new column stores all the time.
Thank you for your presentation, and I want to ask a question about what you suggest for startups or for beginners, as a person who has a big experience in...
As for beginners
For the very beginning, I mean.
Oh, for the very beginning. For startups. Well, I had my own startup, and we did it with servers in my living room. Startups. What we have today is an infinite amount of technology available for you to use in the cloud. So I would never buy your own server. I would never buy your own email systems. I would use what's currently available and pay for what you can afford. That gives you a lot of flexibility, particularly Azure in the .NET space is particularly good at providing the function services in a cloud as opposed to instances in a cloud. Spend only the money that you need to get the job down. Pay yourself first, research your product, and find somebody to market it. So, when I had my own startup, I was the technical geek. I had a sales and marketing partner who all he could think of was how people were going to buy this. And we were successful because he did that. Otherwise, Tim and I would be sitting back in Australia with this wonderful LL2 parser that parsed old programming languages that generated Java and .NET, and we probably would have done one project with it.
Hello, thank you for your presentation. So my question is how new technologies appear on your radar. I assume that you do not test everything new that you see that may fit your needs or improve something.
Okay, so I want to test everything. There's nothing like having a new toy. So I finally got a GPU-based server into Adform that's mine, and nobody else can touch it without my permission. So what I do is I read a lot. So I read InfoQ. I go to QCon at least once a year, and I talk to all of the vendors, and I filter out the sales bullshit, and I focus on the technology. What can that do? How can that make us faster, better, stronger, quicker? So I read a lot, and then I play with it a lot. So as an architect, if you have that title, you must continue to code. If you stop, then you cease being valuable. It's like being a carpenter who builds houses and then owns his own building company and never touches a hammer or a saw again. You have to keep your hands dirty. Yep.
Thanks for the presentation. I wish my uncle was given the same advice as you did. I'm probably gonna get a lot of hate for this question, but it seems that initially your system was mostly Linux-based, but you also kind of have to run all those virtual machines with Windows. And the question is, how did you end up using .NET? Why was it chosen?
Okay, so actually it was .NET first. Adform was originally written on Windows servers, and it built up by that. You get to a point, though, where you want to take advantage of the Linux stack and use it. So that's why we switched. So we started in .NET, and then we added Linux underneath. And if I get my way sometime in the future, we'll get rid of the VMs and we'll use containers.
I have a question, not directly related to technology. But you mentioned if you have a title architect, so you need to keep your hands dirty. So I'm just curious, what is the ratio between technical activities you're taking during your working day and some kind of management work?
Oh, gosh. Well, first of all, I hate management work. I hate having to produce another presentation to tell the people everything I've just told them a few months before. I hate going to another flaming status meeting. I hate all of those things. So what I do is each day I take 2 hours where I am uncontactable. And in those 2 hours, I take new technology and I examine it. So some part of my job, I'm drawing pictures and writing documents so that people understand the thoughts that I have and can communicate them. The other part of my time is I'm going, oh shit, I don't know anything about Node.js. I just recently learned Node.js because I had to. I don't know anything about GraphQL. I recently learned that. So I take that time, I embarrass myself, I feel stupid, but at the end of the day, I feel like I've achieved something because now I know the technology. So it's about, I would say I take about 20-25% of my time to keep my hands dirty. And if I'm too busy, because I have no life, I do it at home in my apartment. So I have a 6-node Raspberry Pi cluster that runs Spark. Not very fast, but it does run Spark. I have little robots that walk around that do Arduino type things. And I code sometimes. You know what it's like when you think, I'll just take this one piece of code and change it, and it's now 3 a.m. and you go, I've almost got it working and it's 5 a.m. That's what happens. So, guys, I'm nearly 60 years old, and this is what I've done my whole career.
Okay, thanks.
All right, guys. Let's thank Peter for the great answer.